Hello, everyone. Thank you for joining us today. My name is Greg Binder, Member Services Manager here at AGU. Welcome to this Atmospheric Sciences section webinar from the past into the future, part 2 of an 8-webinar series featuring speakers from their sessions at the 2019 fall meeting. Today's webinar features Sue Grimmond from the University of Reading in the UK. Sue's presentation is entitled Urban Climates, from Clouds to Cloud Commuting. Our second presenter today will be Guy Brasseur from the National Center for Atmospheric Research in Boulder, Colorado. Guy's presentation is entitled Ozone Depletion and Recovery. Before we get started, just a couple of housekeeping items. Each presenter will get 25 minutes to present with a 5-minute Q&A period at the end. You will have the opportunity to ask questions using the questions functionality of the GoToWebinar control panel, or you can raise your hand using the icon in your control panel. This webinar is being recorded for archive purposes. With that, I now hand things over to Sue. Welcome, Sue.
Thank you.
Hold on one second, Sue. I'm going to make you the presenter. All right. You can begin, Sue.
Okay. Thank you. I'd like to thank you for the opportunity to give this presentation. I'd like to acknowledge my co-authors. I'm going to focus a lot on London because London has had a lot of repeated urban climate studies, and we're also going to see that there are a lot of repeated themes. So by 1801, London was a megacity. In fact, it was the largest city in the world, and it was to remain so until 1925, when New York became larger. So London is in the southeast of the United Kingdom, and Reading is about 50 kilometers away from the centre of London. Heathrow, which maybe most of you, if you know London, will recognise, is on the east side of London. So Helmut Landsberg's book, Urban Climate, which was published in 1981, starts with a history of urban climate, and not unsurprisingly, the first aspects that are considered relate to air quality. And the first mention is to London, but to Rome, sorry, and after that was all associated with London, in particular associated with trying to ban coal burning. So we see that in 1273, 1306, Elizabethan times, and then also by John Evelyn. John Evelyn was concerned in 1659 with both urban form, but also with planting trees and with banning coal. If we turn to today, we see that the Greater London Authority, which has responsibilities for air quality in London, is still concerned with both green trees or planting trees, green vegetation, and also air quality. So air pollution and planting trees has been a repeated theme in London. One of the other reasons London has had sort of a long tradition of urban climate is associated with the Royal Society. This, with members across Europe, were concerned with developing instruments and thinking about, how should scales work, what should the standards be, how should we actually observe weather, and these were being reported to the Royal Society in terms of regular meetings and in their publications. One of the critical things about the Royal Society was at the time between 1780 and 1857, it was located in Somerset House, which is just still today just north of the River Thames. So in this lower image here, we see Somerset House looking towards Parliament buildings from the roof of King's College London. This is what it looked at the time that the Royal Society was located in here. This arch is still present, but now there is an embankment to stop flooding. So there's a road that runs across here. Why this is important is because there was a temperature sensor located outside of the Royal Society buildings. It was of interest for regional climate studies, but Luke Howard, who's renowned for clouds, but also is regarded as sort of one of the founding fathers for urban climate, was taking measurements also at various places around London as he moved from place to place. With that, he published 3 volumes of book called The Climate of London, one of them 200 years old this year. And in that, he identifies 2 things. One is the urban contamination of meteorological records, and the other is thinking about the magnitude and cause of the urban effect. So he identifies that the temperature is being modified because of the artificial warmth induced by the structure of the city, and also the crowded population and the fuel of fires, so today we would think about that as both the form of the city, but also the functioning of the city.
Hey Sue, I have a comment. Somebody's saying that the audio is off. Can you make sure you're
off?
Are you muted, or are you make sure the green icon, the speaker icon, is showing green?
It's green here.
Okay, that's fine. I can verify. Thank you. Continue, please. Sorry for the interruption.
Sorry. So one of the other things Landsberg also reports is the first use of the word heat island in the English language, which he attributes to Manley in 1958 in terms of looking at snowfall. But there is actually earlier mentions also within the Quarterly Journal of the Royal Meteorological Society looking at that. But it had been used earlier in the century in the German literature. Cities have been important for a whole series of different types of observations. They include Tony Chandler's work in the 1960s, using then state-of-the-art temperature measurements, using sort of Stephenson's type screen measurements with aspirated shields and driving around London. With that, he accounts for variations in topography, but also length of times for the travel, and then can look at both minimum temperature and maximum temperature to derive maps of that. He wrote yet another book called The Climate of London. Because many universities are located in cities, a lot of instruments developments have also been associated with cities. The early Yorsphere, which was potentially going to be used as an eddy covariance instrument, was tried out within cities, as was the Bowen ratio and energy balance system. The latter was found not to work because of the eddy diffusivity of water and heat not being equal, and therefore not appropriate for the city. So like many other local scale environments, the sonic anemometer and gas analyzer has become a common tool for taking observations. So located high enough above the surface with radiation sensors, we can actually look at energy balance fluxes. So we can look at, for example, the turbulent sensible heat flux and see its relative importance to the latent heat flux, and see how that varies as urban form varies between different cities around the world. Because of the strong variation in cities in terms of their land cover, thinking about the amount of area that is built and is vegetated, it's not surprising then that the urban area has also been where a lot of consideration has been given to what is within the footprint or what has actually been measured. So Hans-Peter Schmidt's early turbulence source area model to look at the footprint or what characteristics are being observed within the turbulent sensible and latent heat flux footprint, or similarly for radiation, considering, is the roof being seen, is a shaded or sunlit area being seen, or similarly for thermal remote sensing, trying to relate that to satellite remote sensing. So most micrometeorology traditionally came from the sort of Kansas prairie, where the grass surface was small, so the roughness elements were small, and was very easy to locate instruments above the roughness sublayer within the inertial sublayer or the constant flux there. In cities, this is much more challenging, obviously, because the roughness elements, the buildings, the trees are much greater. So using both eddy covariance sensors in the real world and also using wind tunnel studies, there's been a lot of effort to try and determine, where in the conceptual diagram should that dotted line be between the roughness sublayer and the inertial sublayer, to make certain that we're actually taking local scale observations, and things like Monod-Nabokov similarity theory could be considered. So today we regard it to being about 2 to 5 times the height of the roughness elements to be appropriate. New instruments have been designed and used, and one recent sort of example is scintillometry, starting to think about other methods of determining turbulent heat flux. So the first time for large aperture scintillometry was by Laguarde's work in Marseille in France. The beauty or advantage of the scintillometry is instead of having a footprint or source area that's biased by the measurement site, that we have a receiver and a transmitter, and the center weighting of the source area means that we have some freedom about where we put the sensors as long as they're high enough. So using both infrared and millimeter wavelengths, we can determine both the sensible and latent heat fluxes. So work by Helen Ward has allowed us to look at different wavelengths and therefore determine the structure parameter for heat and moisture, and then to be looking at how Bowen ratio fluxes vary and also how they might vary relative to the eddy covariance. That allows us to then have a look at, for example, with different footprints associated with eddy covariance and scintillometry to compare across scales the turbulent sensible heat flux across large time periods. Using multiple path lengths, again back in London, so here's Somerset House where the Royal Society was located, but we also had a sonic anemometer system and 3 paths for scintillometry. We can start to look at the variability within the central city line of turbulent sensible heat flux. Using that, we can look at, for example, variations through the day between summertime and spring relative to winter and autumn, and look at differences between days of week, between weekdays and weekends, and see, as we would expect, higher sensible fluxes in the weekdays associated with anthropogenic heat flux and what we see during the weekends and associated with wintertime associated with heating at higher latitudes as we have in London. We can relate the vegetation fraction of the footprint of the scintillometry. So as the vegetation fraction gets larger, the turbulent sensible heat flux gets smaller, or in the reverse, as the building fraction gets larger, the sensible heat flux gets larger. And then using that and looking at the residual within the surface energy balance and radiation, we can relate that to heating degree days. So as the heating degree days get larger, we have a higher residual that we can associate with this anthropogenic heat flux, and also increasing CO2 fluxes. So again, directly measured. But observations are obviously not sufficient to be able to characterize all of the city. We've got to, for a whole variety of purposes, whether for weather, climate, or for applications, be able to think about modeling across the city. So we live in the roughness sublayer where it's very complex. We have 3-dimensional scaling of the atmosphere where people will cross the street to get into the sun or the shade. If we look at the local scale, we have a series of neighborhoods such as a low residential neighborhood, or a tall building neighborhood, or an industrial area, or areas of parkland. So this patchwork of neighborhoods creates the urban area, and in response we get the whole urban boundary layer. So to characterize the city for a whole variety of different purposes, we clearly will end up with a range of different models, from the very simple, such as what might be needed in a climate model, where we would just try to get some of the urban characteristics regarding things like albedo or roughness thing. In numerical weather prediction, often today we use a infinite canyon that's starting to take into account some of the building morphology, and the more complex models may actually have integrated vegetation, anthropogenic heat flux, and actually have intersections, but still are very simple and relative to realistic buildings. So to characterize the city for modeling, we need to understand the urban morphology, the nature of the roughness, the land cover variations, the variations in anthropogenic heat, the changing phenology characteristics, and the urban hydrology. One of the unified model systems or seamless systems is the that the Met Office uses, and within that allows both weather weather predictions and climate predictions. And the land surface scheme within that is Jules. That has two urban schemes. Mauritius, a 2-tile scheme, and the best 1-tile scheme. The simpler one is used in climate, and the slightly more complex is used within the weather prediction. So for characterizing the southeast of the UK at climate scales of the order of 10 kilometres, we see London clearly being present, but very highly urbanised. At the weather prediction scales of 1.5 kilometre, we see sort of a greater gradation of London. But if we look at using the GUF data, which is from DLR in Germany, which uses the Tandem X data that they can get, we see that there is much more urban area present than what either model is picking up. So if we drop down to look at the 1.5 kilometre scale around the eddy covariance site, we can see that the presence of trees or vegetation, roads and buildings, and the presence of the river, and that those are going to vary the characteristics by wind direction. So we can start to evaluate, for example, the Jules scheme offline at Central Business District of London, a residential area of Swindon. And from that, we can see that the Jules scheme performs generally better in suburban Swindon than it does in central London. And it has greater capability at modelling the outgoing shortwave and longwave radiation than what it does the turbulent heat fluxes. It also is better at modelling summer than winter fluxes. This is largely explained by anthropogenic heat flux, land cover, and the morphology. So looking at anthropogenic heat fluxes, we can see, for example, if we look at as the air temperatures become cooler, there's a greater bias in the anthropogenic heat flux, and some of that comes about because of the Jules has a very simplified anthropogenic heat flux. It basically assumes a constant value for each month with no variability either from day to day or within the day periods, and that it doesn't take into account the variability that we would see, for example, within central London or within a residential area. So that means that we end up with strong bias in the winter time and less of a bias in the summertime, and that this would be a very easy way to improve the modelling of the urban environment. In terms of looking at the morphology, so we need to consider within the Mauritius scheme the canyon fraction and the aspect ratio. The way this is done on a global sense, both in the UKV and in the climate modelling approach, is to associate that with the fraction of urban. So the morphology is based on a small amount of GIS data that was determined at 1 kilometre scale for London and then used globally. Although that allows for variations in turbulent sensible heat flux and in storage heat flux, both between the canyon and the roof behaviour, and then also at the grid box, that has significant implications as we change scales out of the weather scale, both whether we go to the future resolutions of higher resolution or at climate prediction scales. In terms of the land cover information, so the actual fraction urban, we've seen that there's a strong bias in the centre of the city, so looking as though there's virtually no vegetation present. And in the suburban areas, we have the opposite, or small towns, where it actually appears to be too vegetated. That results when we look at the latent heat flux, we see in the centre city, there appears to be almost no evaporation. And once we get into the suburban areas or small towns, then there's very high evaporation rates. Both of these are obviously modifying the Bowen ratio incorrectly. So in the centre city, with the very high land cover rates, this is associated with large runoff rates because there's very little water holding capacity, and therefore the urban tiles dry out very quickly. So that means that we end up with a bias with high evaporation rates immediately following rain and then very low evaporation rates afterwards. So up to now, we've been talking about local scale characteristics, but obviously the local scale is also modifying the boundary layer. So using LiDARs within centimeters, we can observe the attenuated backscatter from aerosols, and we can get that at high resolution. So sort of 10-meter resolution, we can observe the attenuated backscatter, and with very rapid sampling of the order of 15 seconds. Using algorithms such as KBAM, we can determine the mixed layer height and start to look at characteristics of how the mixed layer height varies. For example, seasonally, we see, for example, from sunrise that in the wintertime, the mixed layer height is actually higher than what it is in the summertime, but grows to greater height in the summertime, as we would expect. In all cases, the mixed layer height is greater after solar noon. We can also use the ceilometer for its traditional purpose and actually look at cloud cover characteristics, and to be able to look at variations in cloud cover characteristics. So for example, if we have a clear night and then a cloudy day, we actually see the fastest or the greatest growth of mixed layer heights. So we actually end up with the largest mixed layer heights in the daytime associated with those conditions, and the lowest ones, as we would expect, with stratiform cloud. So using attenuated backscatter from ceilometers, we could also use this for for data assimilation. So one of the things that we could do is develop a forward operator that requires to be computationally cheap so that we can actually model the attenuated backscatter. So looking at the physical and optical characteristics of the aerosol masses, and then compare these two to allow us to actually look at the mixed layer height within the model. So using the UKV, so the weather forecast, with the best one-tile scheme, we can start to have a look at both the observed attenuated backscatter. So this is on a very highly polluted case, so the reds indicate high aerosol content, the red crosses are the mixed layer height. So you can see this is smooth because we've got much more information than the more blocky modeled attenuated backscatter. The next plot is looking at the difference between modeled and observed attenuated backscatter, and ideally this would all be clear, but what we can clearly see is that the aerosol is being held close to the surface and the aerosol mass is remaining too large relative to what's being observed. That is, that there's not sufficient mixing within the model. So the surface scheme is not providing enough mixing to the model. In the operational weather forecast model, the best one-tile scheme has been changed to the Marusis, a two-tile scheme. So what we again can repeat this exercise and see that by putting in the Marusis scheme that we're getting improved mixing, but it's still remaining with not sufficient vertical mixing within the model, so that the aerosol mass is still being retained close to the surface. So from this, using this forward operator, we're getting this sense of the three-dimensional behavior of the model and the implications of the surface characterization and modeling schemes. So one of the things then that become critical is to actually provide services, and the World Meteorological Organization is now undertaking development of guidance for integrated urban services and services which are concerned with weather, environment. Those are associated with air quality, climate, water, and related services. This requires a partnership between the National Meteorological Services and cities. So we might have the traditional meteorological services within here, applications across health, air quality, planning, etc., people making decisions, and then communicating, requiring both research and development, but also capacity development. So the cyclical process which needs a whole series of people to contribute to it. So one potential application is associated with city planning. So we would have our classic urban land surface model, but we now need to communicate with planners to look at, for example, their concerns with population energy use and what might be of concern there, and connect that to the things that we might be normally familiar with in terms of meteorology or hydrology. So again, looking at London, we can start to look at how well could we model that. So in London, there's 33 boroughs. They're organized here from the most vegetated or the least urban to the most urban and least vegetated, with varying amounts of population density and anthropogenic heat fluxes. We can then model across the different boroughs and look at the, this is the median Bowen ratio for July periods, and for 2 different years, a very dry year in 2011, 2012. But we can also compare this to observations, so the urban and suburban are actual observed values, and then look at spatial characteristics for those suburbs. Upon having satisfied that the model is working reasonably well, talking with planners, we can work with them to consider increasing vegetation to past garden states, planting more trees, planting different grass, looking at the implications of different climates, looking at how population might be increased by additional buildings, planting, putting the buildings without changing the vegetation or by changing the vegetation, or making more realistic considerations that consider different transport options, different tree covers, to try and look at what might be realistic and what might the implications be for the city, and so that planners might be able to decide what would be appropriate, but actually only be able to put the buildings or the people in realistic places. But as we think about the future, we also need to be thinking about the next generation of modelling. We need to be thinking about observations not only at the microscale, but also in the boundary layer. We need to be thinking of the real world, that we have both small residential buildings, but in central cities of Asian cities, we have buildings that are greater, or many cities, greater than 600 metres tall, so we can't ignore them. We need to be thinking about the next generation of weather modelling. For example, the Met Office is starting to look and running regularly models of the scales of the order of 300 metres, and obviously climate modelling will become higher resolution. That means that we need to be going back and thinking about wind tunnels and observations, and thinking about the challenges of tall buildings, tall building clusters, and thinking about making certain that the realistic characteristics of, for example, Beijing, and how we're capturing it from the IGPP data for Shanghai and Chongqing, all cities of greater than 30 million people, need to be within our models. But we also need to be thinking about how we're going to characterize those processes. So I'd like to finish by talking about, we know that high impact weather exists. It affects a large number of people. We know if we're going to modify a lot of things at global climate scale, then we're going to have to be making changes in cities. We're going to have to be thinking about the sources of greenhouse gases and aerosols. And that's going to involve working with integrated urban surfaces as partnerships across a whole variety of disciplines. There's going to be a whole lot of exciting science challenges to make models realistic, to account for the varying heights, for accounting for vegetation, tall buildings, and people's behaviour. But we absolutely have to have observations. We need to be thinking about how to observe the cities, not only at the surface, but also the three-dimensional characteristics. And we need to be thinking about the theoretical considerations. How do we actually think about the alternatives to the theory when one of similarity theories and others don't work? Thank you.
All right, thank you very much, Sue. Now we're going to open things up for 5 minutes for questions for Q&A. So please raise your hand if you wish, or pose a question by chat or through the question section of the module. I'll give a couple more seconds for somebody to ask a question. Okay, with that, I'm going to hand this over to Guy and to begin his presentation. Go ahead, Guy.
So, first of all, thank you very much to Jim Earle and Paul Newman for inviting me to give a presentation, which will be essentially a historical presentation related to how ozone was discovered, but also how ozone moved essentially from the laboratory to a big societal question, a big geophysical question. In fact, if we look at the history, we have to go back to 1839, when a German scientist living and working in the University of Basel detected some kind of peculiar odor as he was conducting an electrolysis of water. And he believed immediately that this was probably because of the emission of a substance, but of course he didn't know what this substance was. In fact, it took about 30 years to identify that this odor was essentially due to a gas that was composed purely of oxygen. And it is Jean-Louis Sauret, also in Switzerland, but this time in Geneva, who identify the molecule as being essentially 3 oxygen atoms, OOO, or what we could call O3 today. Now, Schönbein, who made the discovery of ozone, had the feeling that ozone should also be present in the atmosphere. The reason he said that is because he had been smelling the same odor as what he had smelled in his lab outside during thunderstorms in a city of Basel. But he never really identified ozone in the atmosphere. And it is really in 1858 that a French agronomist who was working in Rouen, a bit northwest of Paris, Jean-Auguste Houzeau, who detected basically this odor and basically was able to conclude from an experiment that he made involving arsenic and iodine, so a real chemistry experiment, he was able to conclude that ozone was present in the atmosphere and probably a permanent chemical component of the atmosphere, which was, of course, a major discovery. And that built up on basically the concern that ozone was there, needed to be measured. And in Paris, Albert Lévy, who was a municipal chemist working at the observatory of Parc Montsouris, started using basically this chemical technique to measure ozone day to day in a very systematic way between about 1880 to 1906. And this is a picture of the observatory of Parc Montsouris in Paris, kind of an interesting building that was a replica of a palace in Tunisia that was brought for the World Fair in Paris and then moved to Parc Montsouris. It disappeared now. I think it burned maybe a few decades ago. So this brings us, in spite of my, sorry for my bad voice, to the 1920s. Now, ozone was measured near the surface, but the question was, is ozone also present in higher altitude? And a French scientist, a professor at the University of Marseille, Charles Fabry, who was working with his assistant, Henri Buisson, were measuring the absorption coefficient of ozone in the lab, but then said, okay, maybe if we look at the sun with a spectrometer and we measure the absorption in these wavelengths that we have detected as being absorbing by ozone. Maybe we'll be able to measure how much ozone there is in the atmosphere. They made a first attempt in 1913, before World War I, came up with kind of a column depth or thickness of about 5 millimeters, but then they redid that observation in 1920 after World War I and concluded that there was about a 3 millimeter thickness for the ozone layer. Knowing what was the value near the surface, they then concluded that there must have been more ozone high up in the atmosphere, but they didn't know at what altitude. But so the concept of having an ozone layer came up. Now, Dobson in Oxford wanted to go on after Fabry and build a smaller spectrometer that you see here on the slide. It's in Oxford University, still there in kind of a museum. And they basically made measurements at a variety of locations. Dobson felt that it was important to go all over the world, send instruments on all continents, and he measured essentially a few important things. Number one, there is more ozone at high latitude than in the tropics. Number two, there is a seasonal variation in ozone, and the seasonal variation, the peak is at the end of the winter, and the largest value are at high latitude. If you look at what's happening in the southern hemisphere, you just see that there is also a peak, but 6 months later. So that gave us for the first time kind of a general view of what ozone was about. What was interesting is that the largest value were not where the sun was shining with the highest intensity, and that needed to be taken into account in the interpretation. Now, we didn't know what was the altitude still of this layer, but then in Switzerland, Paul Götz, who was working in Arosa at what became the famous ozone observing station of Arosa, was using the instrument of Dobson and following essentially the sun as it was setting in order to try to determine at what level the maximum of ozone was. And he first concluded that it was between 40 and 60 kilometer altitude. That was higher than what we know today, but it was an interesting attempt. And he moved then later on to higher latitude to redo this observation and detected that, in fact, the layer was more located 25 kilometer altitude. Then we moved to the 1930s, and there was in Paris, at the invitation of Dobson and Fabry, the first ozone conference to really try to analyze what had been observed and to understand what had been observed. Now, remember that they found ozone mostly abundant at high latitude. So they called a scientist who was a specialist of polar processes, aurora, particle penetration, solar particle penetration, etc. This was Sidney Chapman, with the belief and maybe the expectation that Chapman would find a mechanism that involved maybe auroral processes or related processes. But no, Chapman came and Chapman said, ozone is probably formed by UV radiation, by solar radiation. And of course, his theory was simple. He introduced essentially 5 chemical reactions that involve only oxygen and that were going to produce ozone if you put that in a model, essentially in the tropical region, but certainly not at high latitude. And mostly in the summer when the sun is intense, certainly not at the end of the winter. So the model of Chapman was not really explaining what Dobson had been measured, but the first calculation that Chapman did showed that the maximum was probably, as Götz has indicated, at about 40 kilometer altitude. It's an interesting time because observation and model show that the maximum is at 40 kilometer. Both are wrong. We know today that it's more at 25 kilometer altitude. And so we have to be careful when we interpret observation with model or try to use observation to justify what models are producing. That's a lesson for a lot of the scientists. Well, it is in fact in Germany in 1934 that Erich Wegener and his son, Victor Wegener, decided to launch balloons and measure from the balloon, unmanned balloon, the solar radiation and detect essentially as the balloon was moving up and then coming down, measuring the spectrum of the solar radiation, they could detect that the maximum ozone was indeed around 25 kilometer altitude in the lower stratosphere. This was then confirmed later on by manned balloon in 1935, I think, when a big experiment took place with two men going up in the stratosphere up to 20 plus kilometer, I think, and were measuring essentially ozone. This was the Explorer 2 experiment that took place. So in the early 40s, we knew more or less how the ozone was distributed in the atmosphere, in the vertical. We still didn't understand why ozone was most abundant at high latitude, but we also had the first calculation. We had first, of course, additional observation that came up in the late 40s by rockets, confirm essentially the measurements of the 30s from balloon. But one of the big issues was really to understand why ozone was most abundant at high latitude. And Dobson worked closely with Alan Brewer in the UK. Brewer and Dobson were asked to understand essentially, in addition to Dobson's work on ozone, to really understand how the water vapor was behavior that was related to the fact that airplanes during World War II were having contrails, and that was very bad because they could be spotted by the enemy. So they tried to understand the water vapor in the lower stratosphere. And with the measurements that they made on water and also on ozone, Brewer proposed a paper to explain essentially how the circulation was operating. And this is a very good example where chemical species that are measured as tracer essentially give us information about the general circulation of the atmosphere. And so this paper provided evidence of a world circulation showing that essentially the chemical compounds, even if they were produced or injected in the lower latitude in the tropics, could be transported up to the polar region and accumulate there. And that was, of course, a way of understanding this long-term, not understood maximum of ozone in the polar region, in particular at the end of the winter, because it was shown that the circulation was stronger, the meridional circulation from the equator to the pole, what we now call the Brewer-Dobson circulation, was particularly efficient in the winter time. Now, one problem remained, and the problem was that if you make the calculation using the Chapman reaction, you overestimate by at least a factor of 2 the amount of ozone that you observe in the atmosphere. Now, we had to wait until 1950 when David Bates from Northern Ireland and Marcel Nicolet from Belgium, who was also my PhD advisor, came up with the understanding that the destruction of ozone that Chapman had been proposed 20 years earlier in 1930 could be accelerated, or what we say catalyzed, by the presence of hydrogen species that were coming from the water vapor and the methane that are present in the atmosphere. And so it was shown that this mechanism was particularly important in effective in the mesosphere above 50 kilometer altitude, but still could not explain the discrepancy that was observed in the stratosphere. Here is the paper by Bates and Nicolet, the photochemistry of atmospheric water vapor. Then, of course, we moved to the 60s. And so in the 60s, there was a lot of concern about the fact that the correction of Bates and Nicolet was not able to reduce the bias in the stratosphere. There was still a big issue. The chemistry was missing in the stratosphere. And we had to wait later, in fact, the 70s, when Paul Crutzen showed that this destruction was not only accelerated by hydrogen compound, but could be accelerated, in fact, more efficiently accelerated in the stratosphere by nitrogen compounds, by nitric oxide. And nitric oxide then was found to be produced from the oxidation of nitrous oxide, N2O. Nitrous oxide is a product of bacterial activity in the salts. So essentially, ozone is produced by solar radiation on oxygen, and it's destroyed by a process that involves the biology, the bacteria in the salts. And so Paul made a big discovery by showing the influence of nitrogen oxide in the atmosphere. Now, very soon after that, a colleague of him at Berkeley, Harold Johnson, who was a specialist of the nitrogen chemistry and almost independently was working on the role of nitrogen oxide versus ozone, was called into a meeting at NCAR in Boulder about the possible effect of supersonic aircraft that the US wanted to develop, in addition to what the British and the French had been already launching, the Concorde, the famous Concorde. So at that time, it was believed that the water vapor would release from the airplane would destroy ozone. But Johnson came, and as a specialist of nitrogen oxide, he showed that no, water vapor is not doing as much as the nitrogen oxide could do. And the mechanism that Crutzen had proposed just a few months earlier could be very efficient to reduce ozone, he believed, by perhaps as much as a factor of 2, reducing the ozone shield by almost a factor of 2, because of the emissions of a fleet of maybe 500 supersonic aircraft that would operate and cruise in the entire atmosphere. Now, this led the community really to think about the stratosphere. There was a huge program called CIAP, Climatic Impact Assessment Program, that was established and that led to a lot of discoveries and new findings about how what we had called the ignorosphere was operating. But this program really led to very good results and good understanding. And in particular, in around 1974, it was believed that, well, the problem of ozone is understood. Well, this was not counting on 2 papers that came up. In 1974, Stolarski and Cicerone, they were at the University of Michigan at that time, suggested that not only nitrogen could destroy ozone catalytically in the stratosphere, but also chlorine. Now, nobody had much thought about chlorine being present in the atmosphere. Chemists knew that chlorine destroys ozone, but is it really an important compound of the atmosphere? Well, Cicerone and Stolarski didn't know. They were worried about maybe a production by the space shuttle, but also maybe after volcanic eruptions. And it is really a little bit later. Here's first the paper by Stolarski and Cicerone that indicated that stratospheric chlorine is a possible sink for ozone. But then Sherry Rowland was attending a meeting in 1972, during which the results of Lovelock on a ship that was cruising in the Atlantic, Lovelock was measuring a strange compound at that time, at least, which we now call the chlorofluorocarbons, organic chlorine. And he found out that there was quite a bit of concentration of these species, and these species could perhaps be a source of chlorine in the atmosphere. And so Mario Molina and Sherry Rowland showed that the major source of chlorine is really probably produced by the decomposition of chlorofluorocarbons. These CFCs are produced by industry, and of course, industry immediately questioned that, saying that those species are extremely stable. That's why they're used, they're not degraded. Well, the model, the one-dimensional model by Molina and Rowland, showed that indeed it could have a serious effect. And as you know, with Crutzen, Molina and Rowland were laureate of the Nobel Prize of Chemistry for that discoveries. Well, that leads us into the 80s. And again, the 80s was full of surprises. First of all, of course, we had now much better observation. We had space observation. NASA developed a huge program, launched a number of satellites, including TOMS. And now we understand, we see in color, essentially, what Dobson had been already detected with a small spectrometer present or distributed in many places of the world. But now we had a much better understanding of what was happening. Satellite brought also much important information about the dynamics of the atmosphere by following essentially the variability of a number of chemical species. First of all, ozone, or for example, methane. Methane is injected in the stratosphere in the tropics, and we see it being transported to high latitude, showing also the presence of large planetary waves in the atmosphere. You see it here from a TOMS total ozone measurement, or providing information about, let's say, tropical dynamics, tropical wave propagation. This has been a very, very good connection between the chemistry community and the meteorology community involved in stratospheric dynamics in particular. And so people like Jim Holton at University of Washington, or Michael McIntyre in Cambridge, were able, by using theoretical approaches, looking at observations from satellite, to really explain how the transport from the tropics to the pole was occurring. And it was a bit more detailed, more complicated than what Dobson and Brewer had first proposed, but essentially their circulation remains valid. What came out of this study is the role, it's what's driving this circulation, and the role in particular of planetary waves in the stratosphere and gravity wave higher up in the atmosphere. And today I think we have a very good understanding of the dynamics of the mid-atmosphere, thanks to a number of pioneers, but also a lot of observation, in particular from space. Well, in 1984 came really a surprise. First of all, probably unnoticed, but still important, a Japanese scientist who was at a meeting in Greece, the Quadrennial Ozone meeting, conference, put a poster somewhere, and he showed that in the Japanese station of Showa, in October 1982, ozone was very low, lower than he could explain. But nothing came really out of this at that time. People didn't really notice it. And we had to wait. This is his paper that was published in the proceedings of the conference. And we had to wait a few months later when the British scientist Farman and his colleagues at the British Antarctic Survey, who had been monitoring since the geophysical year the ozone at the Halley Base Station. Again, fundamental research, not goal-oriented research, but just they were looking. And suddenly they saw that every year in October, the amount of ozone was gradually decreasing. And they didn't quite know why, but of course they knew about Rowland and Molina, Cicerone and Stolarski's paper. And so they had the idea that maybe chlorine was involved, but they couldn't really find the mechanism. There were a lot of discussion about what the mechanism for this large, substantial ozone depletion located only in the polar region was due to. And there were a number of theories that were proposed. This is the paper here by Farman showing those large losses of ozone. Farman had a lot of hesitation of publishing this, but he looked very carefully at his data. He compared with, he put two instruments next to each other to make sure that it was not a degradation of his instrument. And finally, was confident enough that he published his results. Now, NASA was observing ozone. And in fact, NASA had seen, before Farman published his paper, some substantial decrease in ozone, but was not completely confident that it was not due to an instrument drift. And they had then observations from the ground at the polar South Pole station that didn't show this large depletion. So NASA hesitated a bit, finally proposed a paper to a conference that took place in Czechoslovakia in 3 months after the paper of Farman was published. And so the first picture of the ozone hole that was presented at this conference for October 1983 shown on the left. And of course, you see what happens later on, not only better picture, but also larger ozone hole. This was in 2003. Now, the US really quickly responded to the paper by Farman. And because there were a lot of discrepancies between ideas, was it a dynamical problem? Was it related to maybe more nitrogen oxide coming from high altitude because of solar activity? Or was it really, as Farman has already indicated, probably related to chlorine chemistry, to the CFCs? So Susan Solomon came up with a proposed explanation that chlorine that normally should be relatively inert at high latitude when the sun is not there, could be activated on the surface of polar stratospheric clouds. And so she looked at that and essentially came up with a theory, and then went to Antarctica to the NOAA, it's called NOAA expedition, National Ozone Expedition. They had clear view that chlorine was involved. That was then confirmed a year later when the ER2 from NASA measured simultaneously in the stratosphere ozone and CLO, showing a strong anti-correlation. And so the problem was really solved. The CFCs were really responsible. Now, I'm going to finish by showing you just 2 or 3 things. This is the ozone hole from 2019. The ozone hole is still there, but this year we had a very strange ozone hole, very small, probably associated with a large dynamical feature, last warming that took place. It doesn't mean that the ozone hole is disappearing. We expect the ozone hole to come back next year, but there are variability associated with the dynamic of the stratosphere. Now, ozone has been decreasing. Is it recovering? And I'm going to finish by showing you 2 or 3 slides about this. The Montreal Protocol was signed in 1987 to really take action to basically ban gradually, with a lot of amendment to the protocol, the emission of CFCs in the atmosphere. Here are a number of players who were really outstanding scientists who helped to find a solution. Dan Alberton at NOAA, Bob Watson at NOAA, Gérard Mégy at CNRS in France, and then Ambassador Benedict, who was leading the US delegation at the negotiation that led to the Montreal Protocol. And you see here what is expected to be the recovery. Is the recovery already there? Well, it's early to say, but there are a lot of signs that seems to indicate that ozone is recovering. This is how the ozone hole should be behaving in the future based on model. And you see that the data seems to be following the curves that are predicted by models. These are observations of the total column of ozone since 1970 to more or less present. And you see a bend in the curve that seems to indicate that probably ozone is recovering. But if we look now at the CFCs that should be decreasing, it's interesting to show that the decrease in the CFCs has kind of been stopping in the last years, and it's not following the gray line that are the prediction. There is something happening and probably emissions that should not be taking place. And so the community is currently looking at that. Why isn't the CFCs, why aren't the CFCs, particular 11, not decreasing as expected? With a few sites that we have, it's been able to detect that these additional emissions that should not be happening are occurring in Eastern Asia, and that essentially they are seem to appear in the eastern part of China. And there is a belief that they are production that are not declared, that are not supported by the government, but take place in order to fulfill some needs that still exist. And so this is a problem, of course, for the next years to be looking at. So thank you very much for listening to me, and finishing by showing you two simulation of the ozone hole by the NCAR model Wacom, on the left in 2018, on the right in 2019, showing you a much weaker ozone, not only observed, but also simulated. And thank you very much.
Thank you very much, Guy, for your presentation. So now we're going to pause for 5 minutes for questions for Guy, and then we're going to go back to a question that Philip had for Sue after we finish with questions for Guy. So please feel free to raise your hand or post a question in the questions box. All right, first question here. Hi, thank you for your presentation. I missed the beginning part, so I may just miss, but what do you see as the biggest challenges on climate model for going urban scale? Oh, I'm sorry, that's for Sue. Let me go back to questions for Guy here. Hold on. Does IO from the troposphere make it up in the stratosphere to deplete? So that's a question for Guy.
Okay,
Guy.
I'm open. Yeah, okay. So could you repeat the question now?
Yeah, does IO from the troposphere make it up in the stratosphere to deplete? I'm having a little problem with my vision here, but
So repeat it again. Is IO?
Maybe it says, I'm sorry, NO from the troposphere, make it up to the stratosphere to deplete.
No, the lifetime of nitrogen oxide is relatively short. It's not like the CFCs or methane. Nitrogen oxide play a role in the ozone budget in the troposphere, but there they will be producing ozone as opposed to depleting ozone. So what could enter slightly in the stratosphere is the nitrogen oxide that are produced by lightning in the troposphere. But most of the NO that's produced at the surface from, for example, emission by cars or biomass burning do not really enter the stratosphere. The only question is really about the NOx from lightning, but it's very minimal if it ever happens.
Okay. I have a question from Sergio. I'm going to unmute your phone, Sergio, if you'd like to ask the question. Sergio? Okay, I have another question. Hello, and thank you very much for the great history of exploring the ozone hole. I think I have heard about relationship between southern annular mode and the ozone hole, which I'd like to learn more about. Could you please explain a little bit about that?
Yeah, there are dynamical variability in polar region that affect, of course, the distribution of ozone. And so, again, I mean, I didn't talk much about the connection between dynamics and ozone, but ozone is a tracer with a relatively long lifetime. So it's an inert tracer. And so it captures very much the variability that you see, in particular in the polar region and in the lower stratosphere. So you can learn quite a bit about this, about those type of dynamical perturbations by studying and by analyzing the ozone data.
Okay, another question. What will be the implication of increasing carbon footprint in the recovery of ozone, and is this represented in the global models?
Yeah, this is an important question because we just talk about ozone recovery, but we are recovering towards a situation that is different from what it used to be. Climate will be different. In other words, when we started depleting ozone, let's say 1960, the question is, are we going to go back to that situation or to another situation? And the result is that we're going to go back to another situation because there will be much more CO2 in the atmosphere. The stratospheric temperature will be reduced. It will be cooler stratosphere. And also, what is interesting to see, we see that very much in the southern hemisphere, where, of course, the ozone depletion is large because of the ozone hole. It has an impact on the on the dynamics of the atmosphere and change a number of weather patterns. In particular, for example, the location of the jet stream, the location of the perturbations. And so, what the models are showing is that the recovery of ozone will tend to move back the dynamics where it used to be, but the CO2 increase will try to basically stop that to happen, or at least to reduce the intensity by which the dynamical recovery is occurring. And so the models need to be looking into that because it's a good example where the simultaneous increase in CO2 and the recovery of ozone, which acts differently on the dynamics, will be competing one versus the other, and what's going exactly to happen depends very much on how fast the ozone will recover, and also how much the CO2 will increase in the atmosphere. So it's a very interesting topic to see how the changes that we expect from chemicals, CO2 and ozone, will affect the dynamics, in particular in the southern hemisphere.
Okay, thank you. We have a question from Linda. Was China a signatory country to the Montreal Protocol?
Yes, yes, and you know what I was mentioning is not in terms of the CFC's release, production and release. It's not something that's supported by the government of China. The government of China is after those people. They're trying to find those people. This is all done to smuggle CFCs and by very local people, probably. I'm told they do that in their trucks, and the government is trying to find them and to bring them to court. So China has signed the Montreal Protocol and wants it to be applied.
Okay. Another question: Why the ozone decrease so dramatically from 2018 and 2019?
The ozone has not decreased that. Oh, you want the difference between 2018 and 2019? Is that the question?
Why it decreased so dramatically from 2018 to 2019?
It has not decreased so dramatically from 2018 to 2019.
Okay.
If you're talking about the ozone hole was much weaker in 2019. And that's because on that particular year, the dynamics of the atmosphere was much more active. There were more waves propagating. That happens once in a while. We saw it also, I think, in 2003. And you disturb essentially the polar vortex, create more mixing, and so the ozone hole was much smaller in 2019 than it was in 2018. So what's going to happen next year? Well, the normal situation is a non-disturbed situation, and so we could expect that 2020 will look much more like 2018 than 2019, statistically speaking, unless, you know, again, it's a dynamically perturbed year.
Okay, here's a question for both of you. First, Guy, and then for Sue. What is the main issue that needs urgent attention to improve air quality in climate simulations?
Air quality in climate simulation or in climate simulation?
And climate simulations.
Okay, let's say a word about the air quality. Of course, that's a very long subject, a very complex subject. It's clear that we understand to a large extent what is causing air quality, in particular high ozone level near the surface. We also understand, of course, to a large extent why particles are present in the atmosphere. And all that is very much related to the emissions. Emissions at the surface associated with human activities. China is an example, India is an example, where at the moment we have high emissions. But we can also see, when we look at China in particular, that measures are taken and then the pollution gradually but rapidly goes down. And it's clear that we are on the way of making strong progress. It's important that we do this progress because according to the World Health Organization, about 4 million people die prematurely every year, 4 million from air pollution, outdoor air pollution. You know, at the moment we're talking very much about the coronavirus, but it's great, we should talk about it. But we should not forget that air pollution takes more people in the world. And of course, it's permanent. It's not happening for 3 months. It's happening all the time. but it's important that we take action by reducing a number of emissions, and that requires, of course, a complete change in the economic system, in the way we, in the industrial system, in the transportation system, in the way we organize and create our cities. And so I'm sure Sue will want to add something about that.
Okay. And for Sue, do you have an answer to that question?
Your microphone is not on.
Hold on, let me unmute your microphone. Okay, there you go, Sue.
Thank you.
This is our last question, then we're going to have to wrap it up.
Yeah. I mean, obviously, Guy's answers of, and expertise is much greater than mine in terms of air quality related work. The challenge in urban areas is to actually know about the details of the emissions at the high resolution, but also in terms of the urban meteorology. And I think that is, and the challenge, one of the challenges is how to go from the lack of information in an urban environment, whether it is the land cover information, the emissions, the complexity of the surface, and to identify what actually needs to be taken into account. The other aspect is the three-dimensional characteristics of the city, is that the emissions are not just at one level, but at a variety of levels, and how that occurs. But that requires theoretical considerations as well, in terms of just, what gets transported out and into the boundary layer versus what gets entrained back into the city. But that's at a much smaller scale. Climate is obviously interacting with the city, but at the global scale, we also need to be thinking about what it's going to be transported through.
All right, thank you, Sue and Guy, for joining us today. This concludes our webinar. We'll have the webinar archived within a few days and posted to the Atmospheric Sciences Webinars webpage. Thanks to Jim and Paul for helping to organize these webinars. If anybody is interested in learning more about the atmospheric section or finding out how they can get involved with great activities like this webinar, please reach out to Jim Hurl or Paul Newman or to Rob Braid, our AGU's Director of Engagement and Membership. Thank you all for attending and have a great day, rest of your day.
Thank you for listening.
Okay,
Thank you.
bye-bye.
Bye.